All right, welcome back from spring break. I hope everybody had a nice time. So part of your welcome back is that you've got an exam on Thursday, yeah, and an assignment due because, you know, I don't want to get you too relaxed. Let's just talk briefly about that exam. So the printed formula sheet that I gave you during the last exam, the same equation sheet is going to be provided for this next one. It's posted on MU Online if you want to have an advanced look at what's there. You are going to have both paper calculations and then also a question where you need to use water gems. And so please bring a laptop computer with water gems installed. I haven't yet fully decided what that question is going to look like, but I have done that sort of thing in the past, had a water gems question on the exam, and the students generally liked it because, you know, after you've designed an entire water network and optimized it, then generally there's a pretty good level of familiarity. So it's just kind of rewarding you for that knowledge that you've already acquired. So that's going to be 48 hours from right now. Any questions about the announcements? Yeah.
The water gems question, when we submit it, will we print it?
Great question. Yeah. I think probably what I'll have you do is zip your files. You know, because when you create a water gems project, there's lots of files that it creates. Maybe 3 that have to be there, and it also creates a couple backups. And so what I'll have you do is a zip archive. And so let me show you what I mean by that. If we go into a folder where there's some files, let me create a new folder here. And, you know, this is part of the important thing is you have to be able to know where those files are going to be and put it in a folder where there isn't anything else. So you just create like a subfolder in maybe your documents file or something. And so I've got this new temporary directory that I just saved. And so let me put a couple of things into that temporary directory. All right. I'll put this PDF file and also save my presentation slides there. And then the reason why I'm going to have you zip it is, number one, because then you only have to upload a single file to MU Online. But then the other reason is that zipping reduces the file size quite a lot. And for whatever reason, the way that Water Gems works is it creates a couple of database files that are empty and very large in size. So what you'll have to do is just right-click on the folder, send to compressed zip folder. Well, I guess I can't do it right there in the root of the C drive, so it's offering to put it on my desktop, and that's fine. Okay. You won't get these error messages on exam day. Oh, it doesn't like the dash. So let me close this. Okay, so take away the dash. It doesn't like. All right, let's see if, so I'll highlight these two, right-click, send to compressed folder, and then this would be the single one that you upload for the exam. So I'll give you the reminder on the exam paper of what you need to do, but you'll write the answer to the question on the page, and then so that I can look at what you did using Water Gems, you'll also upload an archive of the files that you create to solve the problem. Make sense? All right. Good. Let me open this back up. Well, today we are going to do some of our time here in the classroom, and then we're going to go down into the lab. It's been a while since we were in the lab. I've got a short demo planned for us today. So let's begin by talking about the Columbia River. And it's one of the biggest hydroelectric projects in the United States. I was just looking up some statistics on it before I came to class, and the Grand Coulee Dam, which is just west of Spokane, they put a really enormous dam across the river, and it creates enough electricity for 4.2 million households. It generates more than 21 billion kilowatt hours per year, and so it's an enormous amount of electricity that's produced. And you can see that you know, there's a couple of different spillways at the dam, and that's what we're going to be talking about today. At first is the relationship between the spillway height and the water surface elevation upstream. Ordinarily, you wouldn't have water flowing down the face of the dam because you're not able to capture the energy associated with that. You'd only use the spillway when there's so much water flowing through the river that you've completely overwhelmed the capacity of the ordinary flow through the penstocks and the generator. We did a similar discussion of this last semester in fluid mechanics when we were talking about the dam in North Dakota. So the spillways are only used very rarely, but when the water levels get high, it's much better to have kind of an engineered method of the water overtopping the dam rather than for it just to happen on its own, where the water would be finding whatever the lowest point of the dam is and flowing over without a specifically engineered spillway. When the water is going down the spillway, it's flowing at supercritical conditions because that's a very steep face, and the water gains a lot of velocity, and then when it gets to the bottom, it still has all of that kinetic energy tied up in the velocity head, and it goes through a hydraulic jump. After the exam, we're going to talk about hydraulic jumps, do the calculations, and we'll go back down into the lab and do a demo related to hydraulic jumps. Today, though, we're just talking about spillways. And so one of the reasons that spillway elevation is so important is that there is a lot of land upstream that is going to be affected by what spillway elevation you choose. You can think of the spillway elevation as kind of the maximum height that the water level is going to be in the reservoir that's upstream of a dam. Let me just kind of indicate the dam itself is around here, and so there's a lot of the river that's downstream of the dam, and so cities that are along the dam that in the past, if the water flow was unregulated, they're protected from flooding because of the dam. But then upstream of the dam, there's a lot of land that wasn't previously underwater that is underwater now. And so one of the calculations that's pretty important is trying to keep track of the elevation of the spillway, because there's a lot of things upstream that could be submerged if the spillway height is too high. Now remember that ordinarily the water isn't going over the spillway, so it could be years and years before the water levels get high enough that the people upstream are going to be affected by the spillway crest elevation. So what this diagram shows is that, in a way, a spillway behaves like a sharp-crested weir. Here on the diagram, it's showing the actual physical cross-section of a spillway, and then it's showing this theoretical weir. We're going to look at a sharp-crested weir down in the lab today, so you'll kind of get a feel for what that looks like. But what this drawing is saying is that the capital H here is the water elevation from this theoretical sharp-crested weir up to the water surface. But for actually measuring the physical elevation of the spillway crest, H sub D is, I guess we could say, 89% of H, because below the spillway crest to the location of the sharp-crested weir is about 11% of the overall H height, and so what is above that is the H sub D. So working in BG units, we have this equation that relates the length of the spillway, and so L, the length of the spillway that we're talking about, would be this distance. You can see the cursor here in the Grand Coulee Dam that has a very, very long spillway. And so L is kind of the distance into the page that we can't exactly see in a figure like this. And then H sub D is the water elevation above the spillway crest up to where there's going to be a little bit of drawdown as the water approaches the spillway, as the velocity starts increasing and you've got that convective acceleration in the non-uniform flow zone. But then once you get upstream some distance so that the water isn't being drawn down, you're able to measure the H sub D. So just to get a feel for how these calculations kind of fit together, let's consider this example where we know the length of the spillway for this example is 300 feet. So that would be the width of the dam, effectively, or at least that portion of the dam that water is flowing down. In a 100-year storm, we know a certain flow rate is going to be going over the spillway, 38,000 CFS. And there are structures upstream at an elevation of 4,350 that we can't have submerged. And so during the planning process, they'll identify what portion of this upstream river basin can be submerged, and then the areas that are going to be preserved, even when the dam is built. And so what we're going to do here is just calculate what elevation should the spillway crest be set to so that the water level upstream never exceeds 4,350. So here what we're using is the equation where the h sub d is what we're going to be calculating. We know L, we know Q, and we're trying to find h sub d so that we can use that h sub e distance and then calculate the elevation of the spillway crest. All right, so let me pause for a moment. Hopefully you brought your calculators today and can crunch through the numbers here and identify what elevation is correct for the spillway crest to be built. So what we're doing is we're solving for h sub d with a given flow rate of 38,000, a given weir length of 300 feet, and then once we find out h sub d, we can subtract that from the given elevation of 4,350. So 4,350 is the water level. We want to find out how far below that the spillway crest should be built. Okay, so let's take a look at that solution here. Just rearranging to solve in terms of h sub d, what we get is it should be about 10 feet of head up above that spillway crest. And so then the spillway crest, therefore, should be 10.06 feet below the given elevation, the water elevation. And so it should be built at 4339.94 feet. Now, you'd like it to be as high as possible, because remember the power equation that we looked at in fluid mechanics last semester. The power equation says that the flow rate times the unit weight of the water times whatever head you have available is going to affect the amount of power that can be generated. And so the higher the elevation difference is between the upper water surface on the reservoir and the lower water surface in the river downstream, and the higher the difference, the more electricity you can generate. But, of course, the higher the difference, the more land area that's going to be inundated by the water. And so you kind of have to balance the amount of land that can be submerged with the amount of electricity that you're hoping to generate. Any questions on this illustration? All right. So that's a spillway, and what we're going to talk about for the rest of our class period is weirs. And we've already talked about the effect that weirs have when we were discussing obstructions. And so before this obstruction was in place, the water was flowing at its normal depth, and what happened was there wasn't enough specific energy to get up over the obstruction. Remember that there is a maximum height step, a maximum step height that can be allowed that's related to the amount of energy that's available. And the requirement to get up over that step is that you have to have enough energy so that at the very least critical flow can be induced over the obstruction. So what we're going to do is we're going to go down into the lab and observe flow over an obstruction similar to this. what you can see is that the water surface draws down a little bit as it accelerates over the obstruction, and then there's additional drawdown as the water goes over the edge. And so it's a little bit tricky saying exactly at what point over this obstruction you're seeing critical flow. And that's one of the things that I hope we can nail down today is we'll do an experimental comparison of the theoretically predicted critical flow for a certain flow rate and what we observe on the Broad-Crested Weir. Fortunately, our Broad-Crested Weir is a little bit longer than this one, so in some sense it makes our job easier because of that. But you'll notice that in this photo there's some like putty along the sides of the weir, and they've put that in place so that the water doesn't seep around it. And unfortunately, when I went to look at my putty today that I have for sealing off the edges, it's totally dried up. And so we're going to have a little bit of water flowing around the side of the weir, and that'll complicate things a little bit. But I think we'll still be able to do the demo in spite of that. So remember the key principle is that when you have some obstruction that's too tall for the water to flow over it without pooling upstream, then the water does pool upstream until there's enough energy for it to cause critical flow over the obstruction. And so the purpose of a broad-crested weir can be used as a flow measurement device. Open channels can sometimes be tricky to know how much water is flowing through that open channel. And so one of the physical ways that you can determine for a canal or for a river how much flow is actually going through that channel at a given time is to measure the depth at a location that you know it's going to be critical conditions. Now, they work because of the relationship between flow rate and critical depth. For a rectangular channel, remember that if you have a certain flow rate Q and you know the width of the channel B, then you can calculate the flow per unit width. So it would be the flow rate divided by the width of the channel. And so we're talking about some channel where the bottom width is B, and of course the top width would also be B because it's rectangular. And we've got some flow rate going through the channel, and so we're trying to find out on a basis of each unit of width how much flow is going through there. So the critical depth, y sub c, is lowercase q squared divided by g to the 1/3 power. And so these work because there is a known relationship between the depth and a flow rate. And if what you can measure easily, like with a yardstick or some sort of an acoustic sensor that's measuring the depth of the water below a known elevation. If what's easy to measure is the depth and you want to know Q, the flow rate, then that relationship that ties the two together is very valuable. The disadvantage of using a broad-crested weir like this to measure the flow rate is that trash and sediment and debris can accumulate upstream of the obstruction. So there are other flow measurement devices that avoid that disadvantage. And another disadvantage is that it causes pooling upstream. You know, by definition, to induce the critical flow, you have to have an obstruction that causes pooling. And there may be situations where you can't afford for the water elevation to get any higher, like if the canal or the channel that you're using doesn't have any extra height available in it for the given flow rate. So there are a couple of disadvantages, but still they're a nice physical way to directly measure the flow rate. Now here are the equations that relate the flow over a broad-crested weir and the elevation h. You can see in this sketch that what they're indicating h, that's the total energy that's above the step height. And so it consists of, when you've got critical flow, it is the critical depth and the velocity head that's above that. And so here is the energy grade line, and under critical flow conditions, sadly, this sketch isn't to scale because what we know is that the flow depth, y sub c, is 2/3 of h. And if anything, in this case, the way they've drawn it, it kind of looks like the velocity head is greater than the flow depth. But that's not the case. The relationship we've talked about before is that the critical depth, y sub c, is 2/3 of the energy that's there. And so therefore, if you measure the y sub c, you can get the total energy. And with the total energy, you can calculate the flow rate. Now, there is a coefficient of discharge that takes into account energy losses due to friction and turbulence at the obstruction. So this C sub D depends largely on the step height relative to the amount of energy at a given time. And a typical C sub D value is in the range of about 0.66 or so. But it varies depending on how deep is the water and how high is the obstruction. All right, so let's go down to the fluid mechanics lab and let's turn on the flume. I've got the Broad-Crested Weir set up in the flume, and we're going to go through this process of observing the critical flow, measuring the flow rate, and trying to compare the theoretically predicted critical depth to what we observe.